So the first topic of the workshop is hyperparameter search. So we'll be talking about how to do hyperparameter search with DeepHyper. Okay, so let me get the laser. Okay, so we already saw two classes of degrees of freedom, right? So one is algorithm hyperparameters, the other one is architecture variables. And the algorithm hyperparameters are the hyperparameters where we say, okay, fixed neural network, fix the neural network topology, and we want to go and find the best hyperparameters that can result in a high performance, let's say accuracy, inference time, or whatsoever, right? So primarily we will be talking about accuracy, but the set of hyperparameters that are responsible for reaching higher accuracy, and we want to tune them. The whole problem, right? So the problem of both the hyperparameter search and the neural architecture search, and also the training problem, can be formulated as a bilevel optimization problem. Why we want to do that? Because we like formalism. But on the other hand, if we formulate this as a sort of a mathematical optimization problem, then we can bring more rigorous and theoretically sound mathematical optimization algorithms to solve this problem. Okay, and this problem is sort of formulated here. So don't get scared about the equations. It's much simple, right? So think of this lower level problem, which you always do, right? So you take the data, you train the model, and that is a lower level problem. The lower level problem is to optimize the training loss, right? So minimize the training loss by optimizing the parameters of the neural network W, and that is a lower level problem. The higher level problem, right? So the upper level problem is we fix the architecture variables and the hyperparameters, and for each combination of these configurations, we go and solve the lower level problem, right? So this means that the problem is a lot more difficult and expensive, right? So even just think about training, you spend a lot of time, doing training, right? But now we are adding this an upper level problem, and this is a sort of an iterative process where you say, for each combination of hyperparameters and neural net and algorithm hyperparameters and architecture variables, we are going to go and solve the lower level problem, which is done in a usual way, right? And for the hyperparameter search, what we say is, for the fixed architecture variable space, so which means that HA is fixed. Okay, so HA is constant. So for a given architecture, for a given topology, we are going to change HM, so which is the algorithm hyperparameters, and then we are going to repeatedly solve for each possible combination of algorithmic hyperparameter configuration the lower level training problem. That's it. So this is just a formulation, okay? And as I mentioned previously, DeepHyper has different components. For the hyperparameter search, we have different set of algorithms. One is random search, which is often used for large number of parameters. And I have seen a lot of Medium posts and blog posts about doing grid search. If you don't have, if you have more than 3 parameters, 3 hyperparameters, and have more values for the parameter, never ever use grid search. Grid search is terrible. And please don't use it. For large number of parameters, at least try random as a baseline, and we are always very serious about where we are, what we are comparing to. So we have to have a good baseline. But for the package perspective, we will be looking at more sophisticated algorithm. In particular, this is a Bayesian optimization algorithm, and that is the focus of the talk. So the Bayesian optimization, the key idea is shown in this little cartoon. So think of a predictive model. Okay, so think of a predictive model, and you have a training data. So this is one-dimensional input and one-dimensional output. So if you have a training data, right? So the Bayesian model usually, so on the places where you have the training data, it sort of so the Bayesian model starts with fitting multiple functions to the data that you have. Okay, so this is different concept if you're not used to Bayesian modeling, but here is the key, right? So given a training data, it fits multiple models on the training data. Wherever you have the training data, the model forces all these functions to pass through that particular training data. Okay, and because of that, you have almost zero uncertainty in those places. And the farther you move away from the training data, your uncertainty increases, right? So this makes sense, right? So if you have training data, your uncertainty is lower. If you don't have training data in a particular region, your uncertainty should be higher, right? So this is the sort of a 10,000 foot view of probabilistic model and particular Bayesian models. Okay, so the nice thing about probabilistic model is that it's not only give you a prediction, but also uncertainty, right? So its uncertainty is inherently built within the probabilistic model. A prototypical example or well-known example for Bayesian modeling is Gaussian process regression. Okay, so please think about what are the other models that follow this kind of behavior, like fitting multiple models and then trying to use those multiple functions, so to speak, and try to do the prediction. Okay, so in the interest of time, we will not have a discussion on that, but please use the Slack and say, can you think of other type of modeling approaches that follow this sort of framework? Okay. So how does Bayesian optimization work? So that's the sort of the key ingredient. So the Bayesian model, or let's say Gaussian process regression, is the key ingredient. And then once you have that ingredient, like what you do is to use that model in an iterative way. So a high-level overview is shown here in the cartoon on the right, and where you have the Bayesian model. So you have initial data points. So here each data point corresponds to a hyperparameter configuration. Okay, so a particular learning rate, batch size, and so on and so forth. You take some random samples of those hyperparameter configurations and you fit a Bayesian model. Okay, and then using this model, now you have regions that are certain and regions that are uncertain. Now the Bayesian optimization is all about leveraging what it already know and what it doesn't know, right? So it can either sample from regions where it is really confident and sample more here, for example, to reduce the loss, or it can go and sample somewhere here in the hope of, because this is an unknown region, right? By sampling here, by choosing a hyperparameter configuration here, it can reduce the uncertainty, and eventually this can lead to improvement in the accuracy, right? So this is the two concepts. So one is called exploitation, so sampling here, and this is called exploration. Okay, and the point is, it is done in an iterative way. So you start with this from the initial sample, from randomly sampling, and then from random sample, and then what you do is just based on the uncertainty and the certainty, you choose a hyperparameter configuration, and then you train the model for the hyperparameter configuration, and then give the result back to the Bayesian model. Now you put that back, and then you retrain this, and then you retrain it, and then you based on the uncertainty, the new uncertainty and the new certainty, you will sample the next set of configuration. Okay, so the idea is simple. It's iteratively sample configurations based on the uncertainty and the certainty that you have. And the key idea, or the key component here that decides how to sort of trade off this exploration and exploitation is acquisition function. So there are multiple acquisition functions that are supported by DeepHyper, and the most simplest one is the upper confidence bound, and also most robust one, in fact. And you can see that a point is chosen based on the mean mu of x, which is nothing but the predictive mean. So think of multiple functions, and you have a prediction from those multiple functions, which is just think of that as an average, and then you have a standard deviation which measures the uncertainty, right? So given a point, you can compute the predictive mean and the uncertainty, and the beta is a user-defined parameter. So easiest ways to understand this, if you set beta equal to 0, it will only exploit, which means that it will always choose hyperparameter configurations that are predictive to be decreasing the loss. On the other hand, if you set beta to a very large value, it will try to sample hyperparameter configurations that reduces the uncertainty of the model. And you don't want to do one or the other always. You want to sort of do this one and the other one, and you want to balance these two. And that balance is given by this user-defined parameter beta. And by using this UCB function, the Bayesian optimization itself sort of balances the trade-off between the exploration and exploitation. Okay, and the point is, Bayesian optimization is not a new idea, and you can in fact find many different packages to do that. But what is the key aspect here is how to scale it. right? So think of if you have a cluster, or even in your if you have a single node with multiple GPUs, you have like 4 or 5 let's say 4 GPUs ready to train, right? So you can use 4 GPUs to train 4 different models. In that case, you have to have the Bayesian optimization method has to have this ability to sample multiple configurations, evaluate them in parallel, and do that in a iterative way, right? By doing so, you can reduce the time to solution and also the accuracy. So this is the sort of the parallel Bayesian optimization idea, or the parallel ideas or parallel concepts in Bayesian optimization. And particularly, we are interested in this parallelization because our target is not only a small node with multiple GPUs, but also clusters with hundreds of GPUs and exascale machines with thousands of GPUs, right? If that's the case, we can build like 1,000 models at any point of time, and then keep iterating that, and eventually whatever it takes like a week to do this type of methods, we can reduce it to hours, right? So that's the sort of impact that we are aiming for, and we are developing methods within the DeepHyper package. So what is the problem? Why don't we just use the Bayesian optimization and sample multiple points? The problem and the challenge is shown here, right? So let's say this is the evaluation, and again, input and output, and these are the uncertainty bands. And from the uncertainty bands, we can compute the acquisition function metric, right? Based on this acquisition metric, we are going to choose the points, okay? So here it says, okay, large uncertainty, choose this point, right? So one at a time, it's fine. But what happens if you just sample more points in a naive way? So you will sample more points, right? And then for the next step, like so if you have 3 GPUs, if you just select 3 points and you said 3 models, so these 3 models are training at the same time. What is the problem? The problem is waste of resources, because if you sample 1 point here, you don't need to sample these 2, right? You want to sample from a different region, because we already sampled from this region, and if we don't take this into account which is provided by the sequential algorithm, then we have a problem. And the whole point is how to make this algorithm a lot more scalable. And for that purpose, so there are 2 different things that we have to do from the traditional Bayesian optimization. First and foremost, we had to move away from Gaussian process regression. Gaussian process regression, you're doing that on a laptop on a single, 1 model at a time, in an iterative way, it's fine. But if you are doing it in a sort of in a parallel setting, Gaussian process regression is not good. In particular, if you have hundreds of GPUs, Gaussian process regression is terrible because of its cubic time complexity. So that's why we had to move to ensemble of regression trees, which is another type of method. Probably you might have used random forest and so on and so forth. So that's a methodology that we adopt, and compute uncertainty from it. So we improve the uncertainty estimate of it. But the point is, the ensemble of regression trees has a log linear time complexity as opposed to the cubic complexity of a Gaussian process regression. And this is a huge difference when you want to scale, because you want to retrain the model as soon as possible. Otherwise, you have hundreds of GPUs sitting idle. And this very fact of the very process of refitting the Gaussian process regression becomes computationally very expensive as you increase the number of data points. Okay, so that's the challenge first we have to overcome. And the second thing is how to sample points in a more informative way. So let's say you want to sample K configurations, and the way that you do that, you select the point in a typical Bayesian optimization sense, right? So select a point that maximizes the acquisition function, and then what you do is to you sample. So in a typical Bayesian optimization setting, you will have a sort of a gradient-based optimization to select that point, the trade-off, the exploration and exploitation. And we cannot do that in a mixed integer optimization setting. So note that our problem has both integer parameters and categorical parameters, and often few real parameters. In the neural network training, you often, all the parameters that you want to train are real, right? So are continuous. But then the hyperparameter optimization, it's not the case, right? So most of them are integer or categorical parameters as opposed to real parameters. So that's why we have to rely on sampling instead of gradient-based optimization. And then you do that, and then you use something called Kriging Bilevel or a constant layer. So let's say you select a point, and then you send that to evaluation, right, to model training. And then what you say next is tell the model that whatever it predicted, like the predictive mean, is correct. So you lie to the Bayesian optimizer what you predicted is right. So what happens is that then the next sample, because when you lie to the model, its uncertainty will become almost zero, right? So it will go and sort of sample from a different region, right? So given k GPUs waiting for you, and you want to generate k configurations, what you have to do is to sort of lie k minus 1 times to make the Bayesian optimizer move to different regions in the search space. And that's the sort of the crux of the asynchronous algorithm that we have within DeepHyper. Okay, so we have two different implementations. One is the centralized, where you have a single manager where the search runs here and then send the hyperparameter configurations to different workers. Think of different workers as different GPUs, different nodes, where each one of them will train the model and then send the results back to the manager in an asynchronous way. There are a lot of bad synchronous algorithms in the Bayesian optimization literature, and those are not scalable when you're talking about hundreds of different GPUs, right? That's a question for the participants. So think of why the batch Bayesian optimization is not a good thing for scaling hyperparameter search. So please use Slack and provide some answers. We will be discussing that. But so this is everything is asynchronous here. There's a search, and you evaluate configurations, you give that back, and this happens in a iterative way. And we also have a decentralized version, which is like extremely scalable version, where we don't have any manager. So in a distributed setting, if you have one node that is responsible for managing many nodes, that will eventually become a bottleneck. And when we are talking about thousands of GPUs on the exascale machines, this may not be the right approach. So that's why we developed the new approach where each GPU or each node has its own search, and they do the sequential optimization, Bayesian optimization, but each worker sort of transmits whatever it has seen to the other workers in an all-to-all fashion. So each worker knows what the other workers are doing and use that data to sort of refeed the model and generate the configuration. So that's a decentralized version. We will not be talking too much about the decentralized version. We will be primarily focusing on the centralized version. In fact, it's a sequential, one manager, one worker in the collab. So this will be the primary focus of today's workshop. So a little bit of a description on the data set. So what we have is, we will be using this data set for the collab hands-on. It's from the NOAA, National Center for Environmental Information, and we will be using the sea surface temperature data set for the hands-on. So this, the task here is, okay, given 2-month forecast where we have the weekly average sea surface temperature. So look at this is the map. These are the sea surface temperatures. Okay, closer to the Antarctica, it's much more colder, and here tropical, so on and so forth. So sea surface temperature is like measuring the temperature of the entire planet, right? So we have a lot of data on that, and we will be sort of saying, okay, given 2 months of weekly average data, we want to forecast what is the sea temperature for the next 2 weeks. And the typical way that people do is run, there is a really computationally expensive model, use supercomputers to do those forecasts, and it takes thousands of core hours. But what machine learning, in particular deep learning, can provide here is, if we can build the model that can do a good forecast, then we can augment that with the simulation, and we can make the simulation 1,000 times faster. And that is like pushing the boundary of what we can do, even with the largest supercomputers we have. So that is it's a real data set, it's a real problem, and we will be looking at this problem today, both for hyperparameter search, neural architecture search, and also for uncertainty quantification. So I will skip this slide in the interest of time, so Roma will be able to cover this during the hands-on, and thank you.